Okay, so neural networks. Down there we can find the parameters by dividing the weights and the biases by the relative cost function that occurs. In our gradient descent model, we can see the gradient equation by using the calculus methods of minimizing the cost function. No. And not just no because everything that I just uttered was complete nonsense. The reality of trying to learn about artificial neural networks is that many tutorials start off like the one that I just did, throwing out math that the user probably does not know how to use in terms that are loaded conceptually. Whether it be articles or videos, most of my research and learning for these past 8 months has been sifting through all of the garbage that uses words and ideas without explaining them clearly. This is why I think it's so hard to get into the field, and that's why I'm going to try and explain everything from the beginning. First off, what is a neural network? It's actually a lot easier than a lot of people portray it to be. A neural network is simply a computing system that's analogous and based on, at least in some aspects, the human brain and nervous system. That's really all it is, an attempt to model human thinking and processing in computers. This is a human neuron, and this is an artificial neuron. An important thing to remember here is that the human neuron is only binary. It fires or it doesn't fire. Artificial neurons are on a scale. They can hold any number on that scale, and that is the measure of how active they are. I'll explain more on what that scale is later. For our network, let's say that we have 3 inputs: a square, a circle, and a triangle. The inputs that we are giving it will be on an 8x8 pixel grid, with the following being examples of the kinds of images we would give it. Think of each neuron in the input layer as something that holds a number. Now let's make it so that each input neuron has a receptive field of 1. A receptive field is simply what each neuron is looking at, what they're taking note of, the number that they're going to take on. Since we have a total of 64 pixels in our grid and we have defined that one neuron will have a receptive field of 1 pixel, we will have a total of 64 inputs, each neuron corresponding with each pixel on our grid. This is where we start to see a real distinction between the way humans and machines learn. As humans, we have rules that constitute what squares, circles, and triangles are. A square is a 4-sided object, which is equal on all sides and all angles. The total of these angles equals 360 degrees. A circle is a shape where the distance from the center to any point on the circle is equal, and that any 2 radii have the same length as one another. A triangle has 3 sides, and the interior angles of a triangle sum up to 180 degrees. Computers don't work in the same way if we're trying to teach them how to classify images. You remember when I said that neurons are just things that hold a number? This is where that comes to light. Every 8x8 image that we have to train our model is a grayscale image, where the value of each pixel is within a range of 0 and 1, where the former is black and the latter is white. Any value between 0 and 1 is some variant of gray, more on the black or white side depending on what value it is. Okay, so now we have our 64 input nodes that correspond to each pixel and 3 output nodes that determine whether or not the image fed through is a square, circle, or triangle. Next, we have these things called hidden layers, and these are just the layers of neurons in between the input and output layers. It's important to keep in mind that the number I chose for both the number of neurons in each layer and the number of layers is arbitrary, and if you were to do this by yourself, you'd have to test out multiple different variations of both the number of neurons in each hidden layer and the number of hidden layers itself. But a general rule of thumb is that the number of neurons in each hidden layer should be between the number of neurons in the input and the output. Now that we have all of the layers set up, let's talk about the basic building block of a neural network, the perceptron. Think outside of our structure for right now and simply focus on this image. The different x values are our inputs and the w values are our weights. You can think of these as the connectors of neurons between the layers. To think of this in terms of our structure, imagine if we only had 3 inputs and we were only focusing on one node in the first hidden layer. The values of these weights determine the strength of our connection. That's the best way to think of it right now. Now here's the important part. To find this number, we go through what I like to call the perceptron process. This is my own term, so you probably won't find it anywhere else, but here's how it goes. The first step is to sum up the products of each weight and input, and remember that weights can also take on negative values. This can also be true of the input. but at least not in the example that we have given with the grayscale values, as it is between 0 and 1. Next, we add the weighted sum of taking the product of each input by its corresponding weight and sum it by B, or the bias. The bias is a point of a lot of confusion, especially for beginners in machine and deep learning, and it took me a while to understand exactly what it was. But luckily, this man named James McCaffrey, a researcher at Microsoft, cleared it up pretty well. He says that it is basically an extra weight multiplied by a dummy input of 1. That's all we really need to know about the bias for right now. Just consider it another weight. And as I'm speaking, when I'm talking about the weights and the biases, I may just be saying the weights, considering that it is really just a weight. Step 3 is a little bit more complex because it involves something called an activation function. An activation function is used for two main reasons. The first that you really need to grasp is to keep our activations in a range of values. Remember that our activations are the numbers that each neuron holds. The weighted sum, which now includes the bias, is probably much larger than we want it to be, so we run it through an activation function to simplify it. A very popular example that is used when teaching and implementing neural networks is the sigmoid function, which squishes all of the values that you have for your weighted sum plus the bias between 1 and -1. Instead, we'll be using the softmax function, which places all of the values in the activations in a layer between 0 and 1. All of the values within a layer should add up to 1. The one that the network believes should be the most active will be the one with the highest value out of 1. You can think of it as a percentage. I hope that the diagram of a perceptron makes sense to you now. So, let's add the weights to our neural network. See, now it makes sense. Everything is now interconnected. Each node in the first hidden layer is connected to every other node by a weight in the first input layer. Because each node in the hidden layer has attached 64 weights and a bias, we have a total of 520 weights between the input layer and the first hidden layer. If we were to sum up the rest of the weights in our network, we will have a total of 619. The kind of neural network that I've been describing throughout this video is called a multi-layer perceptron and is actually one of the oldest kinds of neural networks ever created. There are more recent kinds like the convolutional neural network and the recurrent neural network, but we'll save those for another day. I didn't really go that far into how neural networks learn, which is through the process of gradient descent, as well as how we implement that gradient descent through backpropagation. But once again, we'll save those for other videos. Thank you for watching, and I really hope that I gave you some base understanding of how artificial neural networks are structured.